My name is Joshua Rhodes. I'm a PhD student in, the Department of Civil, Architectural, and Environmental Engineering. I work for the Weber Energy Group, which is actually mechanical engineering, so I'm a bit of an oddball over there. But today I'm going to talk to you about an energy audit study that we did. Well, actually, Brent and I co-authored this study. It was my first, journal paper, and Brent helped me out a lot on it. And the project that I'm working on for my PhD is a Pecan Street Smart Grid demonstration project, and so we'll talk about that. So first, I'm going to introduce my research group and I. I'll talk about I'll kind of introduce the problem of peak power demand, because that's kind of what we dealt with in our study, along with energy consumption. Talk about our published results. I'll talk about Pecan Street, and then some kind of future ideas and research where I feel like that I'm headed. Let me see if this works. All right. So a little bit about me. I got my bachelor's in mathematics and economics at Stephen F. Austin State University in Nacogdoches, Texas. I'm also from Nacogdoches, behind the pine curtain. I got my master's in computational mathematics at Texas A&M. I'm here for my PhD in civil engineering. A member of the Weber Energy Group. My interests include systems level analysis of smart grid technology and building physics. Essentially, it's a smart grid in residences is kind of what I like to look at. And I'm also interested in policy, which is interesting with ECAD stuff, kind of the policy, good policy, especially local policy, because policy here might not be good policy there. And so that's also something I'm interested in. And in case you don't know, Weber Energy Group is a group at the University of Texas at Austin, headed by Dr. Michael Weber. And we focus on 4 main areas. The energy-water nexus. Those are very related and are becoming much more apparent as we go through our drought. Dynamic modeling of complicated energy systems, including the smart grid, carbon capture, sequestration, and whatnot. Alternative transport, electric vehicles, natural gas, biofuels, and then the newest one, the nexus of food, waste, and energy, which is actually quite hefty as well. So first I'm going to talk about peak power demand. It's a real problem, especially here in Texas. ERCOT's already warning that the next summer, because of actually lack of water, we possibly are going to have much more rolling blackouts than we did. Well, we didn't have any actually this summer, but we had some in February, if you remember, with our gas grid depressurizing. So this graph kind of shows, and this laser pointer doesn't work well on the black slide, so I'll just talk about it. This graph kind of shows demand and production in the same. Now, the red line is an average summer demand day. It's the average demand. Now, I got to warn you, this is normalized, so the magnitudes here, don't pay any attention to the magnitudes, okay? They're just showing what the shape of it's like, all right? So the red line is summer demand. That typically peaks in the afternoon. ERCOT's peak is between 3 and 7 p.m. Usually in Austin, it's between 4 and 5, 5 or 6, somewhere kind of fluctuates depending. The green line is summer wind speed. So this is actually out in West Texas. This is, we get all our wind generation here in Texas. And then the yellow line is summer solar radiation. Now this is in Abilene. It's shifted a little bit closer to around noon or 2 for here in Austin, depending on which. But the idea behind it is that while renewables are great, they're not peaking when we need them. The solar is starting to drop off, and the wind speed is just starting to come off of its midday lull. And so, as they stand, it's a problem, and it can't just be solved by throwing a bunch of renewables on the system. And so here's some actual data. This is from 19 homes that are being monitored out at Mueller and Pecan Street. Now I'll get to that later, but just to kind of bring it a little closer to home, the lines are a bit different. So the red line is average use of the home. So that's how much that the home is demanding at that given time of the day. So this is for August 1st. This was our first peak day of summer of 2011. We hit 2660 megawatts at Austin Energy between 5 and 6. The green line is solar generation, is average solar generation. All these homes have solar PV panels on them. And then yellow is from grid. So if it dips below 0, that means the house was actually producing at that time. One of the things you can look at is you can see that, again, the peaks are not lining up. And if we zoom in to the actual peak hour, this is when we peaked, they just give you the hour between. So between 5 and 6 p.m. on August 1st, 2011, we hit our first summer peak at 2660 megawatts. You can actually see that during this time, solar, being intermittent as it is, drops out when we need it the most. Right? So it actually drops down, and we lose almost 2 kilowatts on average from all these solar panels. And so then, of course, demand from the grid goes up. I'm not saying this caused the peak. This is too small of amount of homes, but it didn't help. So just also throwing a bunch of solar out there just won't solve the problem either. All right. So and so this is something you might be a little more familiar with. Austin is unique and is one of the few cities in the world that requires an energy audit to be performed on homes before they can be sold. So most, this applies to commercial and multifamily as well. We limit our analysis to single-family detached homes here just for ease of comparison. So most homes over 10 years old must get an energy audit. The idea is kind of to use market forces to increase the energy efficiency of the building. Hopefully, if you're looking at 2 homes, you might, instead of comparing if they have marble countertops versus laminate, you might also look at the air conditioner efficiency. Some of us would hope, some more than others. We'll see what happens. And it's also to address the Austin Climate Protection Plan, which is to reduce 700, that might be 800 now, by 2020. So to that end, Brent and I, we analyzed 5,000 of these energy audits for single-family detached homes. And then I'll talk a little bit more about the procedures. They're good, but they're not perfect. All right, so in the data set we had, there are about 200 companies that were performing these audits. There's a standard form that's given to Austin Energy, who then gives it to any prospective buyers. Many characteristics were visually noted, such as the air conditioner efficiency, window type, etc. And then some were measured, such as attic insulation, delta T, which is temperature difference across the evaporator coil, the cooling coil, the air conditioner system, and duct leakage. Now there are some problems. Auditors assumed air conditioner airflow rates. The outside temperature was not noted for delta T, which can have the outside temperature when highly elevated can have a difference on, it has a difference on the capacity of the system. Walls are assumed to be code when built. Well, that'd be kind of hard. Nobody's going to want you to drill into their wall to see what it is, so that's an assumption we made as well in our paper. And there were no blower door or air change for our analysis. Now that's kind of important because it doesn't matter how efficiently you cool your air if it all just goes outside anyways. It doesn't really do you any good, right? So some of our first results, our first analytical analysis of ECAD data does reveal some opportunities to reduce peak demand here in Austin. Just efficiency alone, just inefficient air conditioner units installed lead to an excess peak power demand of about 205 megawatts. At the time we published the paper, it was before we hit our next peak at the end of August. That was 8% of Austin's peak. I think it was about 7% of the next one we hit, but anyways. Oversized air conditioning units can lead to an excess peak power demand of about 41 megawatts. We'll talk about all these more in a little bit later. Duct leakage leads to an excess energy consumption, average about 18%, and the reduced AC capacity can lead to an excess energy consumption of about 20%. Oh, that's too far. Okay, so the database actually includes a statistically representative sample of Austin single-family detached homes. When comparing this to pre-1990, not 1999 because it's of the 10-year difference. If we compare them to census data, it lines up very well. And some things that interesting of note, you can actually see the lull in construction during World War II and the savings and loan crisis of the late 1980s. So here's a histogram of the installed air conditioners that are in these homes that we looked at. So you can rather normally distributed. And here's the recommendation given by Energy Star or Austin Energy, and here's where we get 205 megawatts of excess peak. These are running at less efficient units, drawing more power to cool the same amount of space or provide the same amount of cooling. So, and then here's a busy plot. Let me try to unpack it for you. So we also ran a sizing calculation of installed air conditioning units based on an industry standard manual J calculation. And I apologize that they're it's in kilowatts of capacity. I know that's something most people, we use tons here in the States, but everywhere else, if you publish something, it has to be in SI units. 5 tons is about 18 kilowatts of capacity, for just a rough comparison there. So along the x-axis on the bottom is the manual J recommended capacity. We took specifics off of the ECAD audits and we ran it through the calculation. Had to make some assumptions and came out with a recommended capacity. And then the actual installed capacity, just a measured, or just off the nameplate of the unit, is on the y-axis. Now the solid line is 100%. So if the unit that's installed actually corresponds to what we measured it should be, it would be clustered around that solid line. The dashed line down below is 75%. There's actually quite a number of studies that show that sizes down to 75% in manual J, when used correctly, can meet the demand in a home. Now, used correctly is using your thermostat like not using it like a switch, more like a valve than a switch, not just turning it off all the time and then turning it back on. You can't floor a Prius and expect it to get 50 miles a gallon. But, and so the dotted line is 120% of manual J. And that's in other studies, that was the mark that they put it at, so we're assuming anything above that is oversized. So if we look at the excess peak associated with oversized systems, it comes out to about 41 megawatts. And just also interestingly enough, if we increase, if we right-size units that are too small, it would add about a megawatt of excess peak to the grid at that time. All right, and then the next one we looked at were duct leakage, and ducts are notoriously leaky. I don't think anyone's going to argue about that there. Austin Energy recommends anything above 10% be fixed. It's a pretty simple to fix. It's a guy who knows what he's doing, a couple hours, and some not duct tape, but the real stuff. Get up there and fix it. But the average home in these studies uses about 18% more energy to cool their house because your air conditioning in your attic. I'm sure all your family heirlooms appreciate it, but it doesn't really do you too much good. And then just for comparison, these are some other studies that measured the same thing, and we're at the low end, but we're kind of there amongst them all as well. And then the next thing we looked at were air conditioners operating under capacity. In sensible capacity measured versus rated, we took 80% of the nameplate efficiency and called that the sensible rated capacity, and then compared that to the temperature difference across the coil and the airflow. Now the airflow, again, that was not measured, that was just assumed, so take this with a grain of salt, I guess. But so we kind of look at the possibly up to 20% excess energy consumption from air conditioners operating under capacity. This can be fouled coils, this can be poor refrigerant charge. That's typically a big one. There's numerous other studies that have actually gone into many different residential units and found that, that things like this can really lead to a lot of excess energy consumption because your air conditioner is only putting out maybe 2 tons when it's supposed to be putting out 3 or 3.5. So anyways, that kind of wraps up the analysis and the results we got from studying 5,000 energy audits here in Austin, or 5,000 ECAD audits. And so I want to move now to what I'm working on now, which is the Pecan Street Smart Grid Demonstration Project. And the energy audit analysis was great. It was a great prequel to the work with the smart grid, and we're establishing kind of a baseline of what's out there and what we think we can do with that. And so I'll kind of talk about a little bit about kind of what Pecan Street is, and then at the end, I forgot to mention at the beginning, but there's a video, a news magazine came and did a video about kind of Pecan Street and smart grid. It kind of explains it a little bit better. So if I don't do a good job explaining it to you, you know what I'm talking about when done, maybe I'll play that, and maybe it's better pictures, it's more fun. Anyways, but so one of the things, Pecan Street comes out of the ARPA funding, which is the American Recovery and Reinvestment Act. There were 99 projects 99 smart grid projects that were funded by this, and Pecan Street is by far the most advanced. Many of them are just radio-controlled thermostats, and I bet a lot of you could tell me how long in here Austin Energy's been doing that. I can't remember, but it's been a long time. We've been doing that for a long time. So, and all the other ones as well, most of all the other ones as well, are also utility-focused. They're utility, more on mass demand response type things. But this is the first smart grid project that is customer-focused. We're looking at to see what does the customer get out of the smart grid? What would make them want to buy in? What makes most sense to them? So to that end, we're going to be monitoring 1,000 homes inside and outside of Mueller, and I'll get to that in just a second. It's 100% voluntary, so that does introduce some bias, which we'll adjust for in our analysis. We were looking at smart electricity, gas, water, and gas. Water and gas, this will be the first time this has been done, and I'll talk a little bit more about that here in a minute as well. We have a high penetration of residential solar. In 1 square mile, we have over 170 installations of rooftop PV. To our knowledge, this is the densest installation of residential PV in the world, really, that we know of. And so a lot of those have been installed in the past couple months. So this summer is actually going to be really fun as far as transient analysis of transformers and other things to see exactly how those perform. We'll be introducing smart appliances, home energy management systems. There's an industry advisory council associated with Pecan Street, includes like Whirlpool. They're looking at introducing some of their smart appliances, Sony, LG, Best Buy, such and such. And then dynamic pricing and information feedback. What information does the consumer need? What do they want? How long do they want it? Do they not want it at all? They want a computer to do it? That's probably how it's going to be, in my opinion, but we haven't done anything. And we do have preliminary approval to set our own pricing schemes as far as electricity goes. Critical peak pricing, time of use pricing. That's not final, but we do have preliminary approval to do so. So we've got a really nice test bed to work with. It's the biggest it's ever been done. And like I tell you, I deal with the data that's coming off of it right now. It's a lot. So I'll talk about a little bit where it is in case you're not sure. So Mueller is at the site of the old Austin airport. You can actually see the remnants of the old runway here. I never flew into this airport, and I was told I was lucky. It was an absolutely horrible airport to fly into. But up in the top left-hand corner, this is I-35, and up here there's it's commercial. There's Best Buy, Home Depot, and also Dell Children's Hospital is also up there. And these are our currently monitored homes. It's a bit of a dated photo. They're starting to push out on the north, I believe. They're starting to do some more construction, pushing up north into the runway there. And then in context to not a typo, the best of Austin, of course, we have Mueller is again circled in red. UT is, of course, in burnt orange. The Capitol is in yellow. Downtown is in blue. And you can see it is very close to everything. This is a prime piece of property that's opened up smack in the middle of town, and hopefully we're doing it right this time. So it's about 1.5 miles from UT, about 3 miles from downtown, per prime piece of property. So all of this that we're doing, we have lots of data sets that we're collecting right now. Some we've already collected, some we're in the process of collecting, some we're ramping up collection on. But we're taking direct assessments, natural gas meter, electric meter, water meter. We're monitoring subcircuits in homes, up to 6 subcircuits per home. Taking some indirect assessments, quantitative and qualitative. We're doing advanced energy audits. The problems I talked about with the other ones was a great exercise to go through that, because now we eliminated the problems that we talked about earlier, so we can do a more robust analysis. And then surveys to catch any other miscellaneous things. So we're trying to get data from all around, and we have a very robust set of data to do analysis on, and try to figure out some of these problems that we have. So we're taking some measurements directly. We're measuring electricity at the whole home consumption, 6 subcircuits per home. Main subcircuits are, of course, air conditioning, electric clothes dryer, and then electric water heater if they have that. Then they kind of diverge from there up to 30 different subcircuits we're looking at. Only 6 per home, but it just depends on what's in the home, obviously. And we're also, like I said, we have a lot of solar out there, so I'm measuring that at 15-second intervals. People have done smart grid projects before, but Austin Energy actually, a lot of utilities have smart meters. They measure about 15-minute intervals. So this is 60 times the granularity than the information that's ever been taken before. At water, we're measuring total home consumption at 15-second intervals, the same with natural gas. This is the first time this has ever been done. So this will be the pioneering data set. So we get to make all the mistakes, actually, and someone else can do it right. No, I'm just kidding. I think we're doing it right. And then this is just a quick snapshot of kind of what data looks like in April. It doesn't really mean too much. So we're getting advanced home energy audits. We call them advanced because they're based on ECAD audits, but they're better, take away the problems that we talked about earlier. We're looking at home orientation, because that's also a very important factor when doing these kind of analysis. Window characteristics, size, type, location, insulation levels. All the homes out at Mueller were built in 2000 or later and built to green built standards. So we have a better idea of actually what's in the walls and what should be there, what better be there anyways. HVAC, heating, ventilation, air conditioning characteristics, size, leakage. We're doing more in-depth analysis on those than done in ECAD audits. Air tightness, taking blower door test at 3 levels at 3 different pressure differences to define the air change rate of the facade. And also appliance information, age, efficiency, and then the standard recommendations as well that ECAD audits put on. So all of these tell us how the home can and should operate. So this is just an academic, or just not an academic exercise, just an exercise to tell us how the home can and should operate. And then with our monitoring, we'll be able to tell how it actually is operating. And then that's why I get paid, because then I figure out what the difference is, right? That's what the engineers do. But anyways, so here's an example of the kind of technology that we're swapping out. So this is one of the water meters that we're swapping out. We're deploying approximately 100 water and 100 gas meters. I don't think I said that earlier. 1,000 electric, but it's a little harder to deal with water, and I can talk about that later if I have time, and with gas. But these will be inside and outside of Mueller. So we'll, like with electricity, we'll get the green-built homes and then the regular Austin building stock. They're gathering information at a 15-second interval, and as compared to opening up the manhole and reading once a month, that is 178,560 times the granularity that is currently being taken at. And so that kind of is an update on the Pecan Street project. Some of my future ideas that I might look at is looking at least in laboratory setting, possibly more, is looking at a low voltage DC residential architecture. Maybe open up the old Edison light Westinghouse debate again, if anybody knows what that is. RVs have done it for decades, and they seem to be doing all right, besides the FEMA trailers that, emitted formaldehyde like nobody's business. And then something else that Brent and I might talk about is the idea of the all-gas house. You've heard of the all-electric house, but I'm kind of interested in the idea of the all-gas house. Especially with micro combined heat and power turbines or fuel cells, the technology is becoming more affordable, and if you can actually use the waste heat that normally just gets dumped out the smokestack in a residential application per se, just the back of the envelope calculation, you could using waste heat from a fuel cell or a turbine, you could actually run absorptive cooling technologies in the residential home and sell electricity back to the grid. You can actually, at least on the back of the envelope, can make a profit. Now that's something that I'll be looking at for possibly more on my PhD, so I haven't really done much in it. So if you don't like the idea, don't yell at me too much, but tell me quietly why you don't like it. And then just some other analysis that's going to be performed by the 20 plus experts at UT. Is not only me. My goodness to know it's not only me. It's much too big of a project to be only one person. We're looking at micro storage at the home or the block level, and that's battery and or thermal. AC versus DC loads. Again, talked about that in the home, but yeah, I talked about that earlier. Might look at, and also one thing I'm interested in AC versus DC loads is the conversion going from, because we're bringing home AC and then convert it to DC for our computers and everything else. Well, we have efficiency losses, like that little block with the apple on it's heating up and it's actually dumping heat into the air, and the air conditioner has to push that out. So if we could sidestep that, maybe that's something that we could increase efficiency overall. I don't know, we'll look and see. Electric vehicle and plug-in hybrid electric vehicle integration and distribution. This is another big one. I didn't put any slides on it, but There are also going to be 100 Chevy Volts that are going to be put out in Mueller as well. Chevy's put those aside, and people have already signed up to take them. So not only with having all that residential solar, we're going to have a bunch of electric vehicles out there, and so, which is a problem if is not done smart. Because if 4 or 5 people on a block get an electric vehicle and they all plug it in at the same time, that's like adding a couple of other houses on that block, and the transformer substations comes all kinds of interesting dynamics to deal with. There are a lot of smarter people than I will be working on that one, but anyways. Optimization of these and other sectors, and novel building materials integration. There are others that are looking at phase change materials in residential applications to simulate more massive structure using the latent heat of change and not just sensible. So before I go to acknowledgements, well, anyways, I would like to acknowledge, I'd like to acknowledge Mr. Brent Stevens, who's a co-author on the ECAD paper, the first results that I showed you. I'd like to thank Pecan Street, the Doris Duke Foundation for writing me a check every month, allowing me to eat. It's a lot easier to do this when you can, afford to do things. Dr. Michael Weber, my advisor. Mr. Charles Upshaw is not here. He also works with me in Pecan Street Data at UT. The Texas Advanced Computing Center. We've already got 90 million lines of data just on 100 homes over a couple months. So we're using the supercomputing capabilities because it would, break this thing in about 5 seconds to try to do that. Go ahead.
Do you have the manual J's that you were talking about you did for the ECAD?
You need me to go all the way back to the slide?
It's up to you.
Go ahead.
I think it's pretty straightforward. So I was just wondering, I think you said you did 1,000 homes?
It was almost 5,000. So there's
5,000.
Yeah.
So what were you able to put in construction values and insulation, change for orientation for your manual J? So I'm just wondering how general were they, or what assumptions were you making?
As far as orientation, we weren't. The values that were for like insulation values and stuff, attic insulation was measured, but walls, of course, weren't. I assume they were code when built, so dug through the old city codes and tried to make the best decision. It's all spelled out in the paper, our assumptions that were made as well.
Okay. And then also, I was just wondering if the ECADs that you looked at, if they were tracking the con audits, were the results basically tracking the con audits as far as efficiencies of the AC system?
Well, we're actually not fully done with the Pecan Street audits. That information is still coming in and putting it in a database form. Seeing that most of them are out at Mueller and built in 2009 later, I'm going to assume, well, they better be more efficient.
Did you have, I know you have external, you have a lot of other homes also outside?
Yeah, well, we do have 100, yes. And so that'll be, I definitely want to do an analysis between the two and validate, and try to validate, definitely try to validate the initial results, yeah. Yes?
This might be a stupid question. It said peak energy demand is to be acquired at 6 in the evening. Is there any data to show why? Or is it demand in homes? Is it in offices?
Well, it'd be,
What's so special about that time?
the question was like, why is peak between 5 and 6? Okay, ERCOT peak goes between 3 and 7, and sometimes it happens differently. This past summer, the biggest peak was between 3 and 4. But it's the curve typically goes that way because some people are still at work and some people are getting home. They're turning on their air conditioner. Maybe they have the programmable thermostat and they have it set at 80 during the day, but maybe at 5 o'clock they have it dropped down to 75. So you actually see a lot more air conditioners running during that time, which in the home are the biggest power draws in the summertime anyways. People come home, flip on lights, flip on their TVs, plug in their phones to charge. It's kind of that part of the day, and it's really hot outside. Like during the peak it was 105 outside, and so that's also when kind of the peak temperature is also happening, so air conditioners are running less efficient, thus longer. So it's kind of a convergence of all that kind of thing. Does that answer your question? Yes.
In your excess capacity for the HVAC units in the J, you talk about potential savings of 41 megawatts. It was like 25%. What's the correlation with that? Is that a correlation of overuse under capacity unit, the unit's working harder to cool. And an over capacity unit, are you assuming people are cooling to excess level or there's a correlation?
Assuming that they're, well, in a overcapacity unit, it's higher capacity, and so it's drawing more power just to cool. For that, we did, for lack of any other data, we assumed a 70% runtime. I'm going to update that soon with data I'm getting from Pecan Street. Actually, during the peak hour, I'm showing that this stuff I just did actually a couple days ago for pulling data. It's running about 87% of the time air conditioners are running during 3 to 7. And so that'll also have to be updated, but that was the best information we had at that time. We're assuming 70% run times before and after with a smaller unit, thus drawing less energy. Same efficiency, but drawing less.
So it's providing more BTUs. The higher capacity unit. It's theoretically running less. It's running, it's cycling more.
Right, theoretically, yes.
Can I answer to that, Joe?
Sure.
So one problem with oversizing a system is that it will short cycle. And so what happens is that you get a huge power draw every time that AC goes on or off. So it's actually not energy savings to oversize it. You get better efficiency if you size it right.
Yeah, and a lot of times there's actually papers that have been written on why people do that. It's because people turn their air conditioner off all day and expect their home to be, you know, when they turn it on to be cooled down in about 30 minutes, and that's just not the way that physics works. So, okay. Yes?
Yeah, can you foresee any big differences in the data that will result if this project were to be put in place in a northern area of the state?
I mean, definitely, their cooling loads aren't going to be near, northern part of the state or of the country. Yeah, I mean, it shifts more to heating, right? And actually, as the U.S. as a whole is actually heats more than it cools. So we're kind of talking about in this analysis, we've kind of talked about just air conditioning down for the southern states, but you know, probably more natural gas usage and other fuels used for heating, oil and whatnot. So that would be something that has to be taken into account for that time.
Does it require more energy to heat a home rather than cool it down?
Overall, we spend more in the U.S. on heating than we do cooling. That's going to depend on temperature differences and efficiencies of units. I don't have those numbers off the top of my head as far as hard numbers. Yes?
Can you talk a little bit about the low voltage DC usage and maybe comment on the efficiency of using a PV array that wouldn't require an inverter?
So that's also another reason why I'm kind of looking at that is, you know, when a photovoltaic cell is producing electricity from sunlight, it's making DC power. Some newer cells actually have microinverters that it comes off of the panel as AC, but those are new and expensive yet. But that's also another loss. But losses in inverters aren't that bad. Okay, I'm trying to remember the order of magnitude that they're at, but well, not order of magnitude, but where they're at. But it depends on how much electricity costs, is if that's worth going towards. If that amount of savings is worth going toward, depends on how much that energy is going to cost you to begin with. But it would be probably more efficient. You don't have to convert it to AC before you put it into your home network.
Is that why low voltage DC?
Yeah, I mean that's kind of one of the reasons. The problem with DC is if you get high, you can have rather large arcs, and so if you have it's more prone to start fires. So that's why we don't do it. But at low voltage, you know, you could. Like if it's like your car, it's gonna, you know, fizzle or sting a little bit, but it's not gonna kill you if you were to touch the bare wires. But I don't know what volts they would have to be, or what the voltage would have to be.
Yes. Sir, I might have a concern, but you mentioned that Chevy set aside a certain number of volts for that area. Are those already being delivered, and why are you using it?
A few, I think 10 have been delivered, and the other 90 will be delivered in the end of June. So we'll get a massive influx right as the summer is starting to peak. So this will be an interesting data set to view at that point. We're already starting looking at smart algorithms for managing that demand, because if everyone on a peak day plugged them in right now, we'd just start blowing transformers left and right. So we don't want to do that. I'm not going to say we would. I'm not a double E. I'm not an electrical engineer, but I'm saying it would put a lot of stress on the grid. Yes?
Are those volts being subsidized in some way for those owners, or?
Yeah, there's a federal rebate of $7,500, and we've matched that. So $15,000 subsidy. Also, solar out there is 40 cents a watt with all the subsidies we put on there. That's why we have 170 installations. That's an order of magnitude less than going and buying it off the shelf. Yes?
Did your study research any transmission line efficiency?
There are other people that are working on that. That's not my focus. Mine's more on the built environment. But there are those that are doing more macro scale, looking at the grid and efficiency and microgrids and things.
Within the Conscious project?
Oh, what? Sorry, say that again.
Within the auspices of the Conscious project?
Yeah, that and more. I mean, we're building a whole model of the entire Mueller subdivision. So. All right. Thank you.